elsewhere. All of that is true enough. But we'll get to that kind of thing a little bit further in. Any questions about this? Here again, the biome framework, sort of breaking the world into types of system, terrestrial system and coastal system, is sort of the basic framework within which the ecosystem assessment proceeds, along with ecosystem services. Did I skip one? No. Species extinction rates. So this is what we might think of as normal background species extinction rates for marine species and mammals. For every 1,000 mammal species, less than one went extinct every millennium. That's the background rate if you look at the fossil record. Currently, the extinction rate is more like, for amphibians and birds and mammals, it's in the ballpark somewhere between 70 and 100 species per 1,000 per millennium. So we're looking at an extinction rate at present that's roughly 1,000 times higher than in the fossil record. Oh, is that right? That doesn't sound right. Oh, well, okay. Yeah, less than 1, so it is right. And the projected one is more than 10 times higher than the current rate. We're projecting the possibility in the future of 1,000 to more than 10,000, even 20,000 species per 1,000. What? Per 1,000. What? This is all species. Extinctions per 1,000 species per millennium. I'm trying to figure out how you could have more than 1,000 extinctions per. I guess that's just to say that it's not even going to take close to a millennium. For these, where does that estimate come from? Anybody know? There are a handful of climate change modeling experiments that have projected something in the ballpark of like a third to a half of all species being driven to extinction by climate change in the next 100 years, something like that. So that's a big part of how we get rates like that. Distribution of species on Earth is becoming more homogeneous. Genetic diversity has declined globally, particularly among cultivated species. That's a point worth noting. It's actually among the plants and animals that we have domesticated and from which we derive most of our food that the loss of biological diversity is most extreme. Okay? We tend to think of the loss of biological diversity as something that happens in rainforests, right? And which is about whatever, monkeys or birds or rare plants, right? But in fact, it's like rice, corn, potatoes, all these staple crops, horses, cattle, sheep, that the loss of genetic diversity has been most severe, most extreme. So ecosystem changes have resulted in, quote, a substantial and largely irreversible loss in the diversity of life on Earth. Characteristics and implications. The effects are not evenly distributed. The harms are borne disproportionately by the poor, increase in inequality, and can cause poverty and social conflict. These impacts may increase the likelihood of nonlinear change in ecosystem changes. They're abrupt, unpredictable, and potentially irreversible. These are all things that the assessment is warning us about. Okay? Hello. Now the battery is so dead in this that I can't even. Here we go. What are the most important direct drivers? So what are the processes that are immediately resulting in these impacts? Okay? And in a moment we'll get to the indirect drivers, which is to say what are the things that are causing these things to happen, right? So habitat change, climate change, invasive species, overexploitation, pollution. These are the kinds of processes that are degrading ecosystems and ecosystem services worldwide. Here's a nice chart straight out of the report giving you a sense of the intensity of the impact on biodiversity from low to very high. The trend at present, are these impacts declining, remaining the same, or continuing, increasing, very rapidly increasing? And this is, again, the 5 major drivers: habitat change, climate change, invasive species, overexploitation, and pollution across this range of biomes. And I guess the thing to note, I don't see an arrow going down except for temperate forest habitat change, which is that little, that's New England again, right? It's that kind of thing where forest is actually increasing. Other than that, every single arrow is either continuing or increasing. In this column, across all of the world's biomes, pollution of nitrogen and phosphorus is increasing rapidly. Most important direct drivers for different types of systems. For terrestrial ecosystems, it's land cover change and new technologies. In 9 of 14 biomes, 20 to 50% of the area has been transformed largely to croplands. Only biomes relatively unsuited to crop plants, such as deserts, boreal forests, and tundra, have remained largely untransformed by human action. In marine ecosystems, the most important direct drivers are fishing. Biological capability of commercially exploited fish stocks is probably at a historical low. About half of the commercially exploited wild marine fish stocks for which information is available are fully exploited and offer no scope for increased catches. The biomass of some targeted species, especially larger fishes, has been reduced to 1/10 of levels prior to the onset of industrial fishing, particularly significant impact in coastal areas, but is now also affecting the open oceans. So, I mean, a lot of large fisheries. And what's a fishery? Everyone know what a fishery is? What's a fishery? No, it's not where they cultivate fish. And it's not just where the fish are. When I say fishery, I don't mean, oh, there are fish in that ocean. A fishery is the combination of the fish and the people who are catching them. Okay? It's the whole set of things that come together in the act of human fishing. So it usually means a certain group of people in a certain place catching a certain kind of fish. And as fisheries decline near shore, more and more fisheries are moving into the open ocean, which is to say bigger boats going farther away, farther out into the ocean in order to maintain a fishery, right? In order to actually have the combination of fish and a way to catch them that makes for fishery, okay? Freshwater ecosystems have been the most important direct driver is the modification of water regimes, invasive species, and pollution. Modification of water regimes pretty much everywhere means dams, building dams. Whether that is for irrigation, whether it's for municipal water supplies, whether it's for hydroelectric generation, or all of the above. Huge percentage of the world's freshwater systems have been dammed. We're accustomed to it here in the United States where we dam virtually everything, so much so that there aren't really that many undammed waterways left. But it's only in the last 50 years or so that has also become the case in large other parts of the world, such as Asia, Latin America, that kind of thing. So, yes, that's all here on the slide. In coastal ecosystems, conversion of urban sprawl, resorts and ports, aquaculture, and industrialization. 30% decrease worldwide of water and sediment delivery to estuaries. One of the things that happens when you dam a system is that the sediment supply doesn't make it to the mouth of the river anymore. It gets blocked by the dam. Everything upstream of that, all that sediment, which is a source of replenishing nutrients to coastal estuarine systems, is interrupted. Not to mention the fact that the floods, which would have brought sediment periodically and deposited it in deltas, for example, typically don't happen anymore or happen in a completely different way. And you can rearrange a system simply by changing the flooding regime. It's one of those disturbance regimes I was talking about the other day. Approximately 17% of the world's population live below 50 meters above sea level and no further than 100 kilometers from a coast. Approximately 40% live in the full area within 50 kilometers of a coast, regardless of elevation. This is just to say there are dense populations of humans in coastal settings, coastal systems. All right, let's take a 5-minute break. Okay. All right. Here we go. Continuing with the litany. Most important direct drivers of these changes. Again, I don't know if you noticed, what are the two most important environmental problems in the world according to the Millennium Ecosystem Assessment in terms of drivers of impacts, negative impact ecosystems? Yeah, maybe? I'm sorry? I mean, if you had to pick two things to be most agitated about from a, what would they be? Water and soil? No, I'm talking about actual, things that are impacts or drive impacts. Yeah. No, although it's related. Yeah? Yes, climate change and nutrient loading. Right? I mean, I'm sorry. I guess it strikes me that the world is agitated about climate change, or at least huge numbers of people are extremely agitated about climate change, and well, they should be. Nutrient loading just doesn't get that kind of attention, does it? It's just not your celebrity cause for the environment. But none other than the ecosystem assessment itself says it's right up there with climate change, global warming, as a driver. And this, again, it's related to food production. It's very much about fertilizers. And so, excessive nutrient loading. World consumption of nitrogenous fertilizers grew nearly eightfold between 1960 and 2003, from 10.8 million tons to 85.1 million tons. As much as 50% of the nitrogen fertilizer applied may be lost to the environment. What does that mean? It means that farmers apply a lot more fertilizer than the plants they put it on use. And they do that for a combination of reasons. One is they don't want to apply too little. Another is they don't know exactly how much to apply, because how much the plants will use depends on factors outside their control, like how much it rains and whether the growing conditions are better or worse, right? A third reason they do it is that it's cheaper to waste fertilizer than it is to produce less food and not have as much to sell in the market. So it's economically rational for them to apply so much fertilizer that as much as 50% of what they apply simply leaches into the water table or runs off in water runoff rain events and ends up in rivers and then ends up running downstream to the sea. Phosphorus application has increased threefold since 1960. Nitrogen loading to the coastal zone has increased by about 80% worldwide and has driven coral reef community shifts. And you've seen red zones, dead zones, these red tides, these areas at the mouth of major rivers such as the Mississippi where there are enormous growing areas where there's no oxygen in the water. And the reason for that is that so much fertilizer is washed into the system and caused so many plants to grow, so much more than they would otherwise, that when they die and they decompose, they consume all the oxygen in the system. And there is no longer anything for plants to grow, for anything to live on. Like nothing can live in that water anymore. And this is the sort of consequence of nutrient loading, okay? And it has tremendous effects on fisheries and water supplies, water quality, that kind of thing. Whoa. So I'm going to have to go back to using. So we've worked our way through the direct drivers. Let's look at the indirect drivers of ecosystem change at the global scale. And these, they say, are population change, change in economic activity, socio-political factors, cultural factors, and technological change. Demographic. Global population has doubled in the past 40 years, increased by 2 billion people in the last 25 years. That is that's the closest the assessment comes to saying the problem here is population. However, they also note that food production in that same time period has more than kept up with population growth. It has increased 250%. About half of the people in the world live in urban areas now, up from less than 15% at the start of the 20th century. High-income countries typically have populations that are 70 to 80% urban, and that is true of the United States, for example. Economic drivers. Global economic activity increased sevenfold nearly between 1950 and 2000. The late 20th century, income was distributed unevenly both within countries and between countries. International trade in goods in 2001 represented roughly 40% of gross world products. So roughly 40% of all the things in the world that are produced, all the economic goods in the world system, cross some international border between production and use. Here we see a depiction of economic growth, 1990 to 2003. You can see that the former Soviet Union and much of its satellite countries, some of the satellite countries actually experienced negative economic growth between 1990 and 2003. Much of the world experienced growth. South and East Asia experienced very dramatic growth. If you then break this down on a per capita basis, you can see that there were places that even though they experienced positive growth rates, such as most of sub-Saharan Africa, when you account for population change, in fact, it was not an improvement on a per capita basis. So you can see the unevenness of this, right? There are parts of the world that are growing rapidly, other parts that are shrinking. There are parts that are growing overall, but shrinking on a per capita basis. You see that this is not, this is a very complicated pattern. It's not somehow simple to characterize, and it's certainly not about some kind of simple relationship to natural resource endowments either, right? Many of the poorest parts of the world are actually extremely wealthy in terms of natural resources, whether you're talking minerals, oil, fisheries, forests, you name it. Economic drivers. Annual subsidies to conventional energy are estimated to have been $250 to $300 billion in the mid-1990s. The 2001 to 2003 average subsidies paid to the agricultural sectors of developed countries were over $324 billion annually. So the subsidies, the government subsidies to agriculture in the developed world are enormous and have a great deal to do, in fact, with those earlier things that have been noted about fertilizer application and about declining genetic diversity of domesticated crops. So this is not the result of some uninhibited free market necessarily. There are a lot of policy drivers involved as well. Technological change. Science and technology are estimated to have accounted for more than 1/3 of total GDP growth in the U.S. from 1929 to the early 1980s, and for somewhere between a sixth and a half of GDP growth in the developed world as a whole between 1960 and 95. The impact of science and technology on ecosystem services is most evident in the case of food production. Much of the increase in agricultural output over the past 40 years has come from an increase in yields per hectare rather than an expansion of area under cultivation. So we've seen it's cropped up here and there along the way in the lecture today. Agricultural productivity has increased faster than population growth. It has been accompanied by, or made possible by, massive increases in the application of fertilizers, synthetic fertilizers, phosphorus, and nitrogen, and these have in turn become major drivers of ecosystem change. So the nexus here is coming back to food production, but not in terms of a shortage or reaching the limits of production or productivity. Rather, it's about intensification and the application of inputs and technologies that have made possible increased productivity, but also have these downsides. Wheat yields rose 208%, rice yields 109%, maize yields 150%, 57% in the past 4 years in developing countries. The Green Revolution, the sort of worldwide effort to make the world's farmers all grow their food the way they do in the United States, is a big part of this story. And we'll come back to that later in the semester. Advances in fishing technologies have contributed significantly to the depletion of marine fish stocks. So there has been a kind of technological arms race, so to speak, in fisheries as well, in which as fisheries decline, I mean, there's a couple of things you can do, right? You can go someplace else. You can build a better mousetrap as far as the technology you're using to catch fish, or you can stay in the same place and try to catch a different fish, right, than you were previously catching. Building bigger boats with more powerful technologies to go further out in the ocean and fish deeper fish more intensively, those kinds of things have all been significant drivers of change in the oceans. So, any questions or thoughts or reflections on that fairly rapid summary of how much humanity is messing around with the environment? Nothing? Does that give you anything different than you were worried about before in terms of the environment? All this is pretty familiar? Yeah? So, except the nutrient loading thing. All right, good. If I can do anything to make nutrient loading a sexier topic for the world, environmentalists to worry about, I'm all in favor of it. Okay, now I want to sort of shift gears a little bit. I want to think about how to think about these things. And then I want to interrogate the idea of ecosystem services a little bit more carefully, or more pointedly. So we'll start with, this is a sort of very simple, very widely used formula for thinking about human impacts on the environment. It's so widely used that you need to know it. You need to recognize it. You need to know what IPAT stands for. And we need to stop and talk a little bit about it, because especially in certain kinds of policy circles, this is the way people like to sort of translate between environmental variables or phenomena like a dying ecosystem or extinction of a species to human drivers. In other words, how do we kind of draw those links and understand them in a conceptual framework? So IPAT stands for Impact, Population, Affluence, Technology. And the formula is, as written here, I equals P times A times T. And this is supposed to help us think. I would ask you, does it help you think? Trying to think about environmental problems in these terms for a few minutes, and ask yourself, does it help you to think about it in these terms? To say, okay, for any given impact, the impact is somehow the product of population. So bigger population means bigger impact. Affluence, so greater affluence means greater impact. And technology. More technology equals greater impact. Does it help? I see one nodding head. That's, yeah.
It's interesting to me that technology is just across the board more impact when it seems like technology also has helped in improving the environment.
Okay. First problem. Technology could have, maybe any given technology might have a plus or a minus sign on it in this equation, right? Sure, if your technology is a bigger boat for fishing, a bigger engine to drive a bigger piece of equipment to dig even deeper into a mine or